Let me just recompile again. There's still 2 errors. Let me load it. So there are some problems with this code that I didn't realize. Let's see if we can find them. I don't know why this, I would think that this code should work. What's this thing? Ah, I see. So this is a Lisp works does not eval when compile top level. All right. So the problem here is that Lisp works waits until, I guess, the end of the compilation unit to actually instantiate these definitions or something like that. So when I tried to do a read time division here, it said that this wasn't defined and so on. So anyway, it loaded now. And so if I do this compute pi, what I do here is, like I said, we have to take out that square root term, which is 640,320. I compute if I want 100 digits or 100 bits, I think I'm computing, then I have this number of decimal digits per term, add 2, take the floor, whatever. I compute this square root thing. Now you'll notice that there's something kind of dumb here. I am computing square root by doing an integer square root of 10005. But you'll notice that I'm exponentiating or multiplying that by 100 to the power of our precision. I say that's dumb because it's more proper if we use actual floating, arbitrary precision floating point arithmetic as opposed to multiplying what we're taking the square root of by 100 to the power of however many digits. So, because obviously this is equal to 2 times the power of this is 10 to the power of 2 times the precision, because we take the square root, which will take off that factor of 2. So that's kind of dumb. And then we compute the binary split version of the series. When we do binary splitting, we're going to get a rational number back since we have sums of rational numbers. And we get the numerator and denominator here, and we multiply by our square root. We invert the numerator and denominator because we're actually computing 1 over the square root of pi, so we need to compute the reciprocal of that, so we do denominator over numerator, and then multiply by this other factor, which is 640,320 divided by 12, I think. Let's see, yeah, 640,320 divided by 12. And that should give us pi. So let's try that. If we do compute pi to 100 or so digits, we get it. 3.141596, etc., etc. We can do, so integer length tells us the number of bits in a number, 334. That sounds right. We can do time, just to kind of see how long if we want to compute 1, 2, 3. So let's say 100,000 digits. I have no idea how long this will take. A second, that's actually pretty slow. But this is super, super general code. Let's see if we can scale it, what the scale factor is. It should be more than 10 because our multiplications have this log n factor, binary splitting adds this logarithmic factor, and then there's just general overhead, which increases that that k constant. So I leave that running. some other things you can do in this library is do Catalan's constant, which is another hypergeometric series represented here. We compute g prime, and to get Catalan, we have to compute 3/8 times that value plus pi over 8 times the logarithm of 2 plus root 3. So we get the kind of fundamental part, but we also need a logarithm in the computation of pi. Zeta 3, which is Apéri's series or Apéri's constant. We can compute zeta 3 using this stuff right here, and so on. This is taking a very long time. I wonder if it's memory. Obviously, when we did 100,000 digits, it computed, let's see, how much was it? 14 megs. So anyway, all of this can be optimized. It's right now working with very general integers. It does all big num stuff. It's doing GCDs everywhere for every single division. It does finds the greatest common denominator to do cancellations. There's just a lot of stuff you can do to optimize this. But this stuff right here will represent the core of how we do our distributed computation on our little mini cluster. So again, while that's computing, let's look at the other stuff that we have. So in order to gain efficiency, and in order to have more control over the efficiency of our program, it may be desirable to sidestep the common Lisp's implementation of arbitrary precision arithmetic precisely so we can, do things more efficiently. So here, 1 second to 120, that is actually a factor of 100 difference, which is pretty bad, and I suspect it has to do with a lot of the allocation. Anyway, so it might be prudent to sidestep Lisp's implementation of big nums. The reason is most of the common Lisp implementations optimize for arbitrary precision arithmetic for, just general use. Maybe you get 100 digits, maybe in the worst case you get to 1,000 digits, but they're not going to optimize for having billions of digits. They're not going to do that. So when we get to billions of digits, we need to care about multiple things. How are the digits stored? Things like cache locality, saving it to disk, and so on and so forth. So we don't get those niceties with, well, I wouldn't say they're niceties, it's just a bunch of extra busy work, but we don't get that fine-grained control by using Lisp's implementation of arbitrary integers. So it may be wise for us to work with our own implementation of arbitrary precision integers. Why in the world am I programming Lisp? I'm not going to answer the very general question of why Lisp, but Lisp is a very flexible programming language. I probably would only get a quarter of the amount of work done that I can do in another language. It may feel like we've been back 30 years. However, most of the languages that you may be using are trying to catch up to Lisp still. That sounds like a very smug statement, but a lot of the typical things like garbage collection, which came, a good amount 10, 20 years after Lisp. Lambda functions, which rarely anybody gets right except in languages that not a lot of people use, like Haskell. So it may feel like we went back 30 years, but I kind of challenge you to see how much of Lisp is understandable to you if you're not familiar with it, and then see if you really do think it's a old, decrepit 30-year-old thing. So garbage collection was invented by Lisp, so why not use the original deal? So anyway, going back to the arbitrary precision arithmetic, we might want to implement our own. And I've done this previously. My first arbitrary precision arithmetic package was written in BASIC, actually. It was originally QBasic, but I went up to FreeBasic. So So I've done it before. It's hard every single time to do it. I've done it a couple times. It never gets easier to implement arbitrary precision arithmetic just because there are so many things that affect efficiency, so many things that affect the layout of things, just lots of different things. The correctness of arbitrary precision arithmetic programs is difficult, and so on. So every single time it's hard, and there's no doubt that when I implement it this time, it's going to be even harder because we're caring about things like storage to disk, whether part of the high precision number is loaded in RAM, and so on. So to the number theoretic transform, I gotta take this line out, I will do that soon, is the typical way to do high precision multiplication. So let's start with addition and subtraction. If we have a big long number and we want to add them together, the way we do that is we represent the digits in memory and we add them together the normal way we learn about adding. We go column by column, add the first column, write the result, maybe do a carry, add the second column, write the result, maybe do a carry, so on and so forth until you get the number. So at most, your number might be approximately double, and you might have to add one more digit at the very end. Another thing is subtraction. Subtraction is the same. We go one column, we may have to take off a digit, or do a borrow from the other one, kind of keep going and borrow, and we might end up, this is kind of difficult, we might get a negative number. So, but it's not too hard. Another thing is multiplication. So we could do multiplication the same way. We write our two rows of numbers, we multiply the first number by every digit in the second number, we multiply the second number by every, and we kind of do all those multiplications and we add them up. This time it's different though. Instead of doing like this column by column addition or this column by column subtraction, we now have to do, if we have n digits in the first number and another n digits in the second number, we have to do n times n operations, because it's easier if I could draw this out, but I'm not going to try to do that. So it's very complex. So for an n digit number, to multiply that by another n digit number, we have to do about n squared. There's actually a little bit, maybe n squared plus n operations or something like that. But by and large, it's going to be a quadratic number. For addition, we only need to do n operations. We go column by column. There are n columns total, and so it's just n. So if we get into billions of digits, let's even write this out to make the point. Format T, 1,000, million, billion. I want this. We have 1 billion. That's a lot of digits. If we want to multiply two 1 billion digit numbers together, it's going to be this, 1 quintillion. There is no way that I can start doing many multiplications that require 1 quintillion operations. So we have to have a smarter way to multiply. One smarter way is Karatsuba's algorithm, which is a clever way of kind of doing divide and conquer. We kind of divide the number into two halves, and we divide each of those halves into two halves, and then once we get down to the individual digits, we have a very, very clever way of kind of combining the result of the multiplication. And what that turns out as having is, instead of having n squared operations with the normal schoolbook operation, Karatsuba gives us n to the power of 1 point, what is it? I don't remember, 1 point something. Let's look it up. Karatsuba. 1.58. So 1.58. So let's look at the difference. Normal schoolbook is 1 billion to the power of 2.